Hello everyone, and welcome to 3 Deviations. In this video, we are going to be talking about related rates. So this might be a somewhat weird sounding topic. And this is really the applied area of implicit differentiation. We're going to be using a lot of the same techniques that we were using last time. It's going to be very helpful. So what would also be helpful is if you do not know about implicit differentiation, please check my video on it. It's one level back, lecture 13. All right, let's get started with a related rate. So what is a related rate? That's probably the first question you have. So a related rate is really when we have rates of change that are related to one another. So let's say that I have a ladder on a wall. So here's our ladder. Well, there's our wall, there's our ground, and this is going to be a fairly normal wall and ground, so they'll all be at a right angle. Then we'll have our ladder hanging, or resting, and then it will start sliding down. But we're not just going to be sliding down this way, we will also be sliding down this way. And because velocities, because we'll have a v prime, we'll have a v there, we'll have a v there. Velocity is derivative of position, so then we're going to have two derivatives, one going down and one going across. So that's what a related rate is. And I think it's probably best if you get the idea of a slope of a graph out of your head for this one, because we're really thinking about rates of change, not necessarily tangent lines, right? All right, so let's go back to that ladder problem. So I'm going to draw a picture. I recommend you do the same with not just this problem, but all related rates problems. It's always very helpful. There's our ladder, and it says that our ladder is 10 meters long. So 10-meter long ladder. And it's sliding away from the x-axis at 1 meter per second. So could write this as x prime equals 1 meter per second. And they want to ask us how fast it is falling this way, so we'll call this y prime. And they want to know how fast it's falling when our ladder is 6 meters away from the wall. All right, so now we've got kind of our picture all set up. Now what we should do is we should just write out what we're given. So we're given dx dt, 1 meter per second. That's our velocity here with respect to time, our x velocity with respect to time, and that's 1 meter per second. The other theorem that we can employ is the Pythagorean theorem. Because this is a right triangle, we know 6, we know 10. That means that this must be 8. So we can say x squared plus y squared equals 10 squared. And that's 100. So what you can tell about related rates is we're really bringing back a lot of those old geometry formulas, and then we're going to start applying calculus to it. First, what we are going to do is we're going to differentiate this whole big thing with respect to time, and that will give us 2x dx dt plus 2y dy dt equals 0, because 100 goes to 0. And because we already know dx dt is 1, because we have 1 meter per second here, that means that we can just say 2x plus 2y dy dt equals 0. So now what we'll do is we will isolate dy dt, and then we will be able to determine what our velocity with respect to t is in the y direction, how fast it's sliding down when our ladder is 6 feet away. So what we are going to do, we're going to solve for dy dt, and that will give us negative x over y dx dt. And now all that's left is a little bit of substitution. We're just going to say dy dt equals negative 6 over 8, because we have x here over y here, times our velocity in the x direction here, 1, and that will be negative 3/4 meters per second. So that's our first related rate example. Let's do another related rate example. This time we're going to do something called the cone problem. This is the other really popular related rate related problem. So with the cone problem, they're saying water is flowing into a cone with a height of 4 meters and a radius of 2 meters. Right after I see that, I should be thinking, I'm going to draw a picture. It's not going to be a good picture, but it's going to be a picture. So that's going to be 2. And then our height is going to be 4. And the rate of input is 2 cubed meters every minute. So we're going to be going up 2 cubed meters every minute. That's our dV dt. And they want to know, when we're at a height of 3, what is our rate of change of our height when we were at 3 meters. All right, so now we can set up our given. We know that volume of a cone is 1/3 pi r squared h. And now what we're going to do, we're just going to solve for r as a function of h. So we'll get r is equal to h over 2. Now what we will do is we will solve again for volume, and we'll omit the r, and that will give us pi over 12 h cubed. And after that, all that's left is some substitution and some differentiation. So when we differentiate that with respect to d, we'll get dh dt equals 4 over pi h squared dv dt, and that will be dh dt is equal to 8 over 9 pi meters per minute once we do some substitutions. So that is how related rates work, and they're very helpful. This is one of the first application-based areas of calculus we've seen so far. We've done a couple other physics problems, but that's really it. But do not fear, there are many more applications to come, especially in the differentiation field in Unit 3, which will be in a couple days. So next time we are going to be talking about how we can use implicit differentiation to take the derivatives of the inverse trig functions. Then we'll have a brief introduction to differentials, and then we will be moving on to the application-based aspect to differentiation.